Hello everyone. I'm here to blow your minds. Someone from Microsoft is going to talk about Linux-based threats. My name's Ross Bevington and I work at the Microsoft Threat Intelligence Center. And what we do there is we collect threat intelligence for the rest of Microsoft. That's about kind of ongoing attacks that are taking place. And we use this to kind of protect ourselves and our customers. I'm here today to talk about Linux-based threats. Why Linux-based threats with Microsoft? Well, things are changing in Microsoft. We're not just about productivity tools anymore. We've got a really big cloud offering. And inside that cloud offering, Azure, over 50% of the virtual machines we host are Linux. And, over the years, we bought companies like LinkedIn and Skype, and those are kind of Linux-based companies. And in the next version of Windows, we're going to be shipping a Linux kernel actually on Windows as well. So, things are changing. So I'm here to talk about how Mystic creates threat intelligence to protect ourselves and our customers. And some of this is, paid for tools. So if you've heard of Azure Security Center, Azure Front Door, or any of the other kind of Azure security platforms we offer, the work here goes into that. But also, we try and provide as much information as we can to the community. Because if we can protect other people, then, by doing so, we protect ourselves. So every minute, Microsoft sees thousands and thousands of attacks. And, my job is to sift through all of these attacks and divine threat intelligence from it, which is, quite a hard job. And we do this to protect ourselves, protect our customers. But crucially, what do we protect them from? Well, this is an example of dark web. This is the Xdebit marketplace that was shut down recently. And on here, you can buy access to RDP creds, and then you can go ahead and do anything you want on that. There are other marketplaces. This is Dream Market, where you may have heard you can buy your drugs and your passports, but also you can buy things like SSH creds. You can buy, RDB creds and MySQL databases. This is a MySQL VoIP database that, you pay them $38 in Bitcoin as of, August last year, and you'll get access to all that VoIP billing records. So a lot of the attacks we see at the non-APT end of the spectrum usually involve the dark web in some form. People are selling creds on there for anything between 30 cents and $5, VoIP billing databases, other databases, and access to that. So what do these attacks look like? Well, here's a a rough example. So first of all, someone gets access to this server, and it might be via an exploit, it might be via buying creds on the dark web, it might be that the attacker has got their own brute forcing infrastructure and has got access to themselves. Once they've got those creds, chances are they won't be using their brute forcing infrastructure to log in. They'll come in via a clean IP address with a valid username and password, and then, start installing their payload. And here's a brief example of the steps that attackers go through, the recon, defense evasion, persistence, and finally, the actual execution. A lot of the attacks we see at the low end of the spectrum are stealing data, they're Bitcoin mining, potentially a bit of ransomware as well. And crucially, the average time of the box is about 7 minutes for a human being, and human beings still do these attacks. But the vast majority of these are automated bots. Now, for the rest of this presentation, I'm not really interested in the automated bots. They have the same script over and over and again. There's no intelligence behind the actions that they do. What I'm interested in is the human beings that are trying to attack Microsoft and its customers. And the really interesting thing about the stuff that we've been able to do is extrapolate how many individual groups or people are actually attacking us at any one time. And it floats between 70 and 120, active groups. Now, whether these are different or changing, it's difficult to say. So yeah, it's worth saying this isn't APT. I'm not focusing on APT on this talk, but a lot of these techniques might be applicable to those same groups. So these attacks present us with a bit of a dilemma. So we can stand up a honeypot to catch these, not a problem. But then what? So we've got this honeypot infrastructure. It tells us about the attack. It gives us, a bit of malware and, some creds that we should already know because we already know the login for the box. Might give us an IP address that's clean. It doesn't answer any of the real questions that, a business wants to answer. Who did this? Where are they? What are they doing next? Why me? How much is this going to cost? What kind of group is this? Is this APT? Is this, a kid in their bedroom? Honeypots don't help us answer any of those questions at all. And my question to you is do we even care about the attack? Chances are it's a coin miner or something like that. Do we actually care? Or do we actually care about answers to these questions? And how can we go about answering them? And I've got another problem as well. Honeypots are actually broken. It's really easy to spot a honeypot, and attackers are doing this all the time. One of the first things I see when an attacker logs into a box is they do a number of different probes, sometimes even before they log in, to check that they're not going to give away their kind of modus operandi, how they're working. You can go on to Shodan and type in an IP address, and that will tell you whether it thinks it's a honeypot or not. And then the final thing attackers usually do, they go onto a box, they port forward out to the internet to what's my IP, and they compare the IP that they've come in on with the IP that data is going out on, because lots of very big honeypot providers, you're spending lots of money to get that juicy threat intel from them, don't want to route their traffic through the IP address that they've come in on. So there's lots of different kind of techniques that attackers use. Next thing, it's really costly to set up a honeypot. Attackers want really fast machines at the moment, and that means you might have to buy a really fast machine or rent one. And the ongoing maintenance is huge, like making sure that the environments are torn down and they're brought up correctly when an attacker gets in. And the process where an attacker gets in, they get some time in the box and then it's torn down itself doesn't really scale very well. Most boxes can only have one attacker kind of running their kind of malware at a time. Now, I'm really worried about giving attackers something for free. If you're putting some honeypot boxes on the internet to be exploited, you're giving them access to real machines for a length of time. And they can coin mine on those boxes, or they can use those IP addresses to brute force the rest of the internet. As a company, Microsoft don't want to create victims. And so running a traditional, what we're called high interaction honeypots, or a VM, is really difficult for us. And the next thing is that we want to kind of apply the kind of tools and techniques we have from looking at APT to kind of these lower end threats. And the biggest problem with a lot of honeypot environments that you can get from, open source or commercial is that they give you lots and lots of data, but they give you no way to process that data. And we want to process that data and actually do something with it, because collecting, all this attacker threat intel data for, no reason is not really helping us. So when we went and looked at developing our own honeypot/deception technology, I wanted to go back to the drawing board. And, first off, kind of what is deception? Well, there's no real good definition for deception. You can go on Wikipedia and you get something wishy-washy. Saying it's emerging, but it's been emerging for 30 years. What I like to think of it is it's kind of understanding the attacker behind the attack. I'm interested in the human being. I'm trying to deceive them, trick them, getting them to do what I want rather than what they want. There's only really two good examples of deception technology at the moment, and that is honeypots and canary tokens. And this is something that I think that, as an industry, we can do a lot more things with. We should be tricking people. We should be kind of understanding their behaviors, moving them around our network as we choose. So I was inspired by, human civilization. We've been doing deception technology for, since the dawn of civilization. And we can be inspired by, salesmen. Salesmen trying to deceive people all the time. They have tools like scarcity. Oh, there's only one of these left. Or, oh no, this has got a problem, but I can fix it this way, including reason why when they're kind of introducing faults. Next up, kind of con men, social engineers. They tell us that we should listen really, really hard, to the other side and use that against them. Casinos, they are experts on the art of deception, and they teach us we need to kind of place services strategically. And we need to kind of give people near wins, but keep them spinning for that big jackpot at the end. And then finally, a real kind of emerging area of InfoSec is game theory. And what that says is that we can kind of treat attacker behavior like a flow diagram. Map their behavior onto a graph. And what they kind of teach us is that actually by having lots of different types of honeypots that look very, very different, we might get better wins from that. And I want to kind of extend this and kind of introduce a concept that I call the fog of war. Now, with traditional threat intelligence today, you just find out the success state. You set up a machine and you try to make that as easy to attack as possible. You install all the tools. You don't want the attacker to leave your box after getting onto it. And that really throws the data off. Like, there are so many different states, different choices the attacker makes that we don't get to see, and that's clouded in a fog of war. Getting to these other states is crucial to understand, what's going on in that attacker's mind when they're on your box, what they're going to do next, what they could do, different infrastructure, that kind of stuff. And as a defender, I want to lift this fog of war so I can get as much information as I can. And I've come up with a technique called fault injection in order to do this. And what that allows us to do is lift this fog of war and find other states that we would otherwise not normally have got to with a traditional honeypot network. So the idea is, relatively simple. Is that we're not interested in bots. We're studying the human being in front of that keyboard. And by injecting faults at different places, commands that don't work, commands that do work, we can get them to move across this graph. In essence, we're kind of trapping them in a maze that we control. And as they move around this maze, or an internet-connected weighted graph, we get to understand and explore what they know that we don't. Now, this might be new infrastructure. This might be that they don't have any new infrastructure. It might be their backup plans. It might be we can understand what their experience on Linux is, whether they know that different commands exist. We want to potentially trick them into giving us more information about themselves, because with that we can find out who they are. And I liken this to kind of tracking the attacker in a maze or the matrix. And we're pushing them around with a bit of cheese. So we built this system, and we've been running it for about a year now, just over a year. And we wanted it to be more than just a traditional honeypot, using some of the techniques I've discussed. Crucially, take this data and use it to protect customers. Another thing is, it needs to be extremely low cost and maintainable. We don't have a team of people that can sit babysitting this kind of infrastructure all the time. We want to put it on the internet, fire and forget. We don't have to worry about, the implications of tearing that up and down. But with an understanding that, tomorrow, the attacks that we see will be completely different. We don't want to rewrite this from scratch again. And the final thing, perhaps the most important thing, is that there can be no ability for us to create victims, whether that's attackers getting on the box and using their tools to brute force other infrastructure or coin mine or anything like that. We need to make sure that the thing we're putting on the internet is safe. So our solution, it's more than just a honeypot, and it's designed to collect maximum amount of attacker-originated data. Any information that's on an attacker's machine, we want that information. That's really great threat intel. And so we've designed a system that tries to pull out as much stuff as possible. Now, we recreated Linux as a simulated environment. This isn't an emulator. This isn't virtualization. This is code that, purports to be the bash shell. We can put hundreds of OS images into this to stand up loads of different things. We could be IoT device for one connection, Ubuntu 16.04 for another connection, other OSs that are really difficult to, emulate and put on our platforms, all these different things. Now, I have written Linux again. We log every TCP SYN packet, which is the first packet that comes from the attacker, because that gives us, crucial information. And we support many, many protocols. Once you've done the hard work of, writing a Linux simulator, you can put SSH on top of that. You can put Docker, you can put Telnet, you can put MySQL, you can put all these different protocols, and they all kind of interop together. To be clear, I have implemented Nano in C#. I have implemented, password, PASSWD. and implemented things like cat and grep. Now, this may sound really, really hard, but, Nano was 500 lines of code. PASSWD, I think, was about 50, and, it goes down from there. And this is one of the tricks that we can do as a defender. We only have to implement commands that the attackers are using. That solves a lot of problems. And the benefit of it being Linux is most commands, when they're successful, don't actually output any kind of text on the screen. So getting something up there very quickly was very, very easy. We've deployed these machines all over the world. So it's in every Azure data center and lots of other vendor data centers as well. And, on premises where we can. And we're collecting kind of huge amounts of data. To try and keep costs down, we use the kind of very bargain basement kind of VM spec, and we can handle thousands of simultaneous logins per second. I don't think we've kind of really got to the kind of max. Whereas most Linux, high interaction honeypots can handle one connection perhaps every 5 minutes. By one connection, I mean attacker logs in and issues commands and that kind of stuff. We can handle thousands and thousands and thousands. And we kind of game the system. When an attacker logs in and they try to enter passwords, we say they're all correct. We're not interested in attackers brute forcing stuff. We want to let them log in. And so, as such, we collect lots and lots of information from attacks that, other honeypots probably wouldn't be able to see. 50 gigabytes a day is what we're currently collecting. We're probably trying to collect that a bit more. And, we want to search this data pretty much instantly. And we do this by putting all of our data into Azure's log analytics platform. And that is, allows us to do near instant searching, and storage is cheap. And then we take the results from all of this and we put it into our security products, but also we take this data, we pull out all the URLs, we pull out all the malware, and we give this to VirusTotal because there's no point us hanging on to it. We want to kind of share this as widely as possible. And how do we collect this kind of attacker data? Well, we're a rogue server, and there's a lot of kind of work out there, prior art, on being, a rogue client. So, I sent this to the server and bad things happen. Well, what if we're a bad server? What can we do if we're a bad server? We're not really bad. We're doing this for good. We control the protocol, and it's really important that kind of I ram home that point. We get to decide how the attacker's client kind of connects to us, and we can ask it different things, and that might give us different data. So in things like VNC or SSH, we can implement extensions that may be not on by default, but if we kind of say that we support, we can get more information. And with that, we can build fingerprints because we've got high entropy data from attacker's machine or attacker's infrastructure. And then we can use that to track these kind of attackers or attacker groups across the different virtual machines or compromised hosts that they use. And that's really, really important. We do some of this by just tracking the first packet, because the first packet that comes from the attacker's machine. It's crafted by their kernel. And this has some really magic fields, like the time to live can tell us how deep they are into a network, how many hops it's taken us to get to them to get to our machine, and the window size and the TCP timestamp. Those fields can be used to kind of work out the attacker's real OS. Once you've got the attacker's real OS, you can start reasoning about how they're working and what they're doing and what infrastructure they're using. So this is really, really important. In the case of SSH, we get things like environmental variables. We get things like public keys, terminal modes, things that you would otherwise not be able to get if you were a traditional high interaction honeypot, because that would involve, writing your own SSH client or adding logging to the one that's already there. In protocols like VNC, this could be the attacker's clipboard. Now, I want to go on to some results now. And before I do, there's a bit of a warning. There are people's hidden faces on this. There's IP addresses. And this is all kind of raw threat intelligence. I don't want you to take this and say, this is a bad guy. Attribution is extremely hard. It's often wrong. And some of these IPs still possibly active. So whatever you do, don't visit them. So, warning over. What does our honeypot actually look like, first of all? Well, here's a kind of a rough idea of what you would get if you SSH'd into a traditional high interaction honeypot today. Now, I've added a canary token in there, which I'll go into a sec, but this is kind of the data you would buy from, say, a threat intel company, all the stuff in green. They downloaded something, they did a bit of recon, and then they executed it at the end. You might get the malware as well. This isn't that useful for me. What happens if that first URL didn't work? So wget returned an error. What does the attacker do now? Well, the attacker has a choice. They could leave the box, they could fix the DNS resolver, or they could go to a different piece of infrastructure. And in this example, which I've kind of welded together from two different attacks, the attacker goes to a different piece of infrastructure. And this happens all the time. This could be a Discord server, Dropbox, something like that. Something that gives us extra information about this attack that we would otherwise not have before. We do things like use psychological processes called the rule of three. And so if this doesn't work, if 2 times it fails, the 3rd time it will work, because we know that attackers will work that way with that psychological principle. The 3rd time they might try and download some source code. This is great. We've gone from from a binary to a source code, bit of source code now. When they try and unzip that, I've injected a fault to say that won't work. Well, why would I want to do that? Well, zip files don't contain very much metadata, but tar files do. So if I can move the attacker to download a tar file, then I could get things like the user that the archive was created, the group it was created under, just a little bit more information. We can make it so when they execute their code, it doesn't work. It's never being executed anyway. This is an entire simulation. But we can also add a bit of scarcity. So telling them, the system's going down, but we'll give a reason why. And it's a UPS failure. We haven't caught you. And so that might encourage the attacker to add an authorized key to the key file. Now, the things we're doing in here from a psychological kind of process is we're building confidence with a disclaimer. That's a bit weird, isn't it? But actually it builds confidence that it's a real system. We have a lure and a big win, which is you're on the billing server. We're including reasons why when we're faulting. We're using the rule of 3. So after 3 wgets, the last one worked. We're enriching that data. We're taking a zip file and converting it to a tar file. And we're using distraction and scarcity to get the attacker to do things they would otherwise not do. We use our custom SSH implementation, which is open source. And we don't just collect agent strings. That's pretty boring. Environmental variables, terminal size, lots and lots of entropy. And we use that to make a hash. And once we've got hash, we can use that to track across different infrastructure. But the most interesting things we do is we take all the public keys that we've seen and we look that up on GitHub. Now, this is absolutely public. You can do that today. Go to GitHub and ask for a list of public keys for all the different users. But if an attacker is unsolicitedly giving me a public key and they've used that to talk to GitHub, then I know who they are. This isn't new. No, this has been kind of donkey's years old. Have a look on GitHub for more information there. And here's an example of someone who did log into my machine with their public key that was also used on GitHub. And what's interesting here is that we get to find out where they live. We get to see they're interested in Go, man, the middle proxies, and the Mirai source code, which is interesting because the honeypot at this point was compromised by a Mirai-based botnet. Other people, this person doesn't have any repos for us to divine any information, but we were able to get access to their username because it's on the front page of the GitHub profile. And once we've got that, we can start exploring that with other social media sites. So you can go onto Instagram and find that person is in Ukraine, and then have a look at their pictures and find, perhaps the machine that was used to attack with. Is this person bad? I've got no idea, but what I can tell you is a public key that they had access to accessed my honeypot. And that doesn't sound good. Other things we do, we use canary tokens. So attackers, break in, they nose around, they want to steal more data. And, if you've heard of canary tokens, they've been used for a long time to signal when an attack has started. But can we use this to kind of turn it around to get more information from an attacker? Yes. We do things like planting files on the file system to try and lure an attacker to kind of download it. So you can see the different directory names, long file name, different date. We use lots and lots of psychological tricks to convince people that that's the file you want. In fact, making the file system look like an arrow. And because we have access to the attacker's kind of operating system, we know what they're coming from, we can kind of make really good lures based on that as well. And what can we do from that? Well, an attacker installs a coin miner. It comes from DigitalOcean, mines Monero. This is all we would otherwise have on a traditional honeypot. But what we can do is feed that environment with canary tokens. This is real, by the way. The attacker downloads, link.txt. They open link.txt on Chrome on their box instead of, the box perhaps they had compromised the honeypot with. And at that point, you can tell, okay, that attacker, is in Romania. And that's really useful for us because now we've gleaned more information than we'd otherwise had before. Other things we have access to, bizarrely, people, proxy their phones and things through honeypots. That's because you can buy those things for proxy on the dark web to get your fast Netflix access and that kind of things. But attackers also do that to connect to C2 environments, and so we get C2 traffic, and so we can find other boxes that are, popped and, have a look at that in a bit greater depth. That also gives us something else that's interesting as well. Here's an example that happens all the time. Attackers have compromised a honeypot environment. They're using it to, port forward to, login.live.com, outlook.com, that kind of stuff. And they want to break into that system by disguising their IP address. But in our environment, we can trap these requests and we can redivert them to our own web server, which is what we do. So now we've got the ability to send arbitrary HTML to an attacker. So that's also really interesting. And if you do a little bit more research, you could send things like, a web-based port scanner to the attacker and get more information that way. Final thing is I wrote a VNC server. This was fun. And we use that to kind of pretend to be industrial control system environments by, changing the desktop wallpaper. And, we've got our bath simulator running as a window in there. Because we've implemented that protocol, we get access to things that we'd otherwise not get. Did you know if you're running VNC, type VNC, real VNC, and you do a copy and paste action while your window is open, your server gets that data from your clipboard, unsolicited. And so an attacker logged into one of my boxes and decided to copy a list of over 1,000 IP addresses they've compromised while the window was open. This is another great way of collecting information from an attacker. Now, one final kind of point is it doesn't all go well for attackers. Spare a thought for the person that spent, over 10 minutes and running 60 commands trying to fix the DNS resolver on my box. Now, this was an earlier version that didn't use the psychological rule of 3, just everything failed. But it tells you a lot about the attacker and the fact that they don't have any other infrastructure. So, to summarize all of this, we use kind of deception technology to kind of enumerate attacker behavior. And we do this to try and protect ourselves and trying to protect Azure. Try and protect the community if we can as well. We develop, alerts based on this, detection of bad IPs, automatic reporting of bad IPs that we see on our IP ranges that, might be a customer's compromised box. It underpins our metrics-based detection approach. So when we're writing detections for our security products, we want to make sure we can detect everything out of our honeypot. We get A+ threat intel based on this, and we try and share this as widely as we can. And where we have built on open source components, we're kind of actively sharing those. And ideally, my boss wants me to share the whole thing with the community. We're not there yet, but we're trying. If you want to see the changes we've made to our the SSH implementation we use, you can check out FXS SSH, and we also detonate some of these things in the Cuckoo sandbox where we've made some changes for help kind of Linux detonation there. 1 minute, 13 seconds to go. Thank you very much.
Thank you for your time, Ross. I think you did just fine. You didn't speed up too much. Ladies and gentlemen, a note of importance. All the slides will be published almost immediately on the website for Ross's talk and upcoming talks. We have about 46 seconds for questions. If you have any, we'll have a go at it. And if not, then Ross is going to be available later on, I'm sure. Buy him drinks, and he'll be more than happy to talk to you.
Exactly. One drink per question.
Questions, please, until the next speaker gets on stage. Come on, deception techniques. Everybody is, yes. There he is, behind you.
Thank you. Yeah, this working? Yes. Really cool stuff over here. And my first reaction after hearing this was, I want to deploy this in my own network at work. But since it's not ready to be released yet, do you have any estimations on that?
You're not the first person to ask me that. My boss asked me that as well. We've got lots of ideas for this technology. We want to make more use out of it. As I said, my boss wants it to be open source, John Lambert, to try and get as many people in the community to help with as possible. We've already released some of it. Long story short, the only way you can get access today is get access to the data, which is either via VirusTotal or by subscribing to our products. But it's something that we're working towards. Anything that can help the community helps us. Usually tenfold times, and we've got a roadmap for it. Unfortunately, you can't share it because I haven't written it. So, yeah, thank you. I'll try.
Thanks, but still, really cool stuff.
Thank you.
Okay, last one. If not, we have the next speaker come on stage. I'll grant one last question. Going once, twice, and thank you very much, Ross, for your time.